This video is about the sample operator. This operator is often used to reduce the size of an example set so that processing can happen more quickly. This is usually done when you're developing or debugging a process, or sometimes you actually have to do it simply to reduce the size of the data so you can fit the processing into the time you have. Now, this approach to sampling usually needs to preserve the relative proportions of labels, but sampling can also be used to change this relative proportion. This is an important consideration for some classification processes which work best with data having balanced label proportions. So we'll start by looking at the three main ways of sampling, and we'll ignore the balancing question for the first three here. So that's relative, absolute, and sample with probability, ignoring the balanced flag. And then we'll do the same again, but set the balanced flag to true and to exert more control over the proportions of the labels. Okay, so here's a process. It makes some data, doesn't matter how I do it, but I'm passing it then to 6 copies of the sample operator. And they are in the order as described at the beginning. So this one is sample relative. So if I look at the parameters here, you can see I've selected relative and a value. This one is absolute and the value. And this one here is probability with 0.9 as a value. These ones here essentially repeat that, but this time I'm setting the balanced data flag to true, and this lets you exert more control over how the classes are represented in the output. So this is relative, absolute, probability. Anyway, let's start with the simpler case. So let's run this. We'll start with looking at the data. So the data is our old friend, the ARIS dataset, and it's got 25 examples, and I've selected 5 vesiculars and 20 setosas, and the IDs are just the IDs from the original data, and I've got rid of all of the other attributes because they just get in the way. So let's start by looking at the relative 0.2 situation, which is this one here. So basically I said relative 0.2, and now what will happen is it will choose a 20% sample from the data. So if we go to the results, this is the result of applying relative 0.2 to the 25 examples, and you can see it's basically chosen 5, which 20% of 25 is 5, and it's basically got the number of labelled data points in the same proportion. So there are 4 out of 20 setosas, which is 20%, and 1 out of 5 vesiculars, which is 20%. Okay, so when you don't care about the proportion of labeled data, it will obviously do its best by the laws of probability, and essentially what you'll get is a faithful reproduction of the original data in the output. So now let's go back to absolute. So this situation is let's sample absolute. So this time it's just saying pick 15 examples at random from the ones presented to it. So we go back to the results. Here we are, and as you can see, it's picked 15, and it's basically represented the proportions in the same way. So setosa, it looks like there are 12 setosas and 3 vesiculars, which is 15 over 25, that's 60%, so it's basically probabilities working today. So you tend to use the absolute one because it's a better, you know the number after, it's easier to calculate it. I tend to use that one the most, to be honest. Now obviously in passing, if we set this random seed now and run it again, we'll get a different set of examples in the output. So if we just learn by heart the IDs of here, so 33, 34, 36, I run that again. Now I've set the random seed to be different. Yeah, so 34's disappeared. So in other words, it's picked different random examples simply by virtue of changing the random seed. So that's just something to bear in mind. I'll turn that off though for now. And then The final one is probability 0.9. In this case, I've set this to, so what this is very similar to the relative case, but it's basically going to let through each example with a probability based on 0.9. In other words, an example will get through with a 0.9 probability through to the final output. So 90% of 25 is about 23. We look at the results. Yep, sure enough, we've got 23 examples. In this situation, all the vesiculars made it, and all but 2 of the setoses. So there's a 90% chance that they made it through. Some didn't, 10% of them didn't. But clearly in the vesicular case there aren't very many, so they all made it, because the 10% is smaller than one of these. So probability is working today. Now let's go to the balanced data option. So we'll look at relative imbalanced first. So we've set the sample to be relative. We've set this balanced data to true. Now what we can do is click on this here, and we can now choose how to represent each class. Notice that it's the class, that's the only thing that really matters in this sampling operation. Now I'm basically saying I want all of the vesiculars and I want half the setoses. So going to the results, sure enough we can see there are all the vesiculars and half the setoses, for a total of 15 examples. So in effect what we're doing is changing the proportion of the labelled data relative to itself, and you might want to do that under certain circumstances if certain problems require a balanced labelled data set. Now of course you're sampling, so you're reducing data. If you don't have much data to begin with, you wouldn't do this. There are other ways, bootstrapping and so on, but this just shows that in principle you can change the proportions here. Okay, so let's go back to the absolute situation. So it's very similar. So I've selected absolute, balanced data, and now I can choose an exact number that I want. In this situation I want 3 setoses and 3 vesiculars. Okay, going back to the data. Sure enough, this time I've got 3 random setoses and 3 random vesiculars. So clearly I've got it's a 50-50 class split now, but obviously I've hardly got any data now, so you wouldn't do that, so you don't have much of it. Okay, the final situation, probability. Again, I'm now going to be able to select by probability, so if I edit the list, I'm basically saying give me 90% of the setoses and all of the vesiculars. So go to the results. So yep, sure enough, I've got all of the vesiculars and 90% of the setoses, which is 20, beg your pardon, 18 setoses out of 20, 90%. Okay. So it's quite a simple operator, and it can do quite a lot, and you will use it a lot actually. I tend to use it most when debugging, frankly, and trying to predict how long things will take. So I'll run this one more time, and I will switch between the original input data, and I'll just go through each of these one by one relatively slowly.